Today topic is discussion topic is DeMorgan's theorem. DeMorgan's a mathematician who know Boolean proposed two theorems that are an important part of the Boolean algebra in partial terms. DeMorgan's theorem provided mathematical verification of the equivalences of the NAND gate and negative OR gate and the equivalency of the NOR gate and negative AND gates, which are discussion in part 3. One of the DeMorgan's theorems is states as follows. DeMorgan's first theorem is follows. The complement of a product of variable is equal to the sum of the complement of variables. Sum of the complement of variables. The complement of product of variable is equal to the sum of the complement of variables. Standard another ways, the complementary of two or more AND variables is equal to the R of the complementary of individual variables. The formulas from the expressing these theorems for two variables is x into y whole bar is equal x bar plus y bar. X into y whole bar is equal x bar plus y bar. DeMorgan's second theorem stands as follows. The complement of a sum of variable is equal to the product of the complementary of the variables. The DeMorgan's second theorem stands another ways. The complement of two or more added variables is equivalent to the AND of the complementary of individual variables. DeMorgan's second theorem, the following expressions this theorem for two variables is x plus y whole bar is equal to x bar into y bar. X bar into y bar. X plus y whole bar is equal to x bar into y bar. This is the basic success circuit diagrams is DeMorgan's first theorem as well as DeMorgan's second theorem. They proving LHS is equal to RHS. DeMorgan's first theorem, when LHS is NAND gate or AND gate plus NOT gate. AND gate plus NOT gate. RHS is two NOT gates, one OR gates. One OR gate. This is the LHS is equal to RHS in the form of the DeMorgan first theorem. Similarly, DeMorgan second theorem, NOR gate or OR gate plus NOT gate. OR gate plus NOT gate is equal to two NOT gates, one AND gate, negative AND gate. negative AND gate. The states the DeMorgan first law formation is x into y whole bar is equal to x bar plus y bar, and expressions for the De Morgan second theorem is x plus y whole bar is equal to x bar into y bar. The proof of the De Morgan first theorem and De Morgan second theorem with the help of the truth table, that is where input is x and y and output is x into y whole bar, and another output is x bar plus y bar, x bar plus y bar. Using circuit diagram, case 1, x is equal to 0, y is equal to 0, resultant output is 0 into 0, 0, 0 bar is equal to 1. Their LHS is output 1, and case 2, x is equal to 0, y is equal to 1, where NAND gate output is 1. Third case, x is equal to 1, y is equal to 0. This is the NAND gate. NAND gate output is 1. And last, fourth condition, x is equal to 1, y is equal to 1, where NAND gate output is x into y bar is equal to 0. This is a LHS inputs, LHS outputs. Next, RHS, same inputs, output is verified. X is equal to 0, y is equal to 0, negative OR gates, then answer is 1, output is 1. Next, x is equal to 0, y is equal to 1, then negative OR gate, answer is output is 1. Next, third condition, x is equal to 1, y is equal to 0, negative OR gate, the output is 1. And the last condition is x is equal to 1, y is equal to 1, then output negative OR gate is x bar plus y bar, that is equal to 0. When where LHS output is equal to RHS output, that is x into y whole bar is equal to x bar plus y bar, where De Morgan first theorem is states and proves with logical circuits and help of the truth table. Help of the truth table. Next, second one, De Morgan's second theorem. De Morgan's second theorem, LHS stands for NOR gate, RHS stands for negative AND gate. Negative AND gate. Verifying De Morgan's second theorem with help of truth table, where xy is inputs variable. First case is LHS, where LHS proving De Morgan's second theorems. First case is x is equal to 0, y is equal to 0. Then a resultant of the NOR gate is x plus y whole bar is equal to 1. Second condition, x is 0, y is equal to 1. NOR gate resultant x plus y whole bar is equal to 0. Next, third conditions, x is equal to 1, y is equal to 0, NOR gate output x plus y whole bar is equal to 0, and last condition x is equal to 1, y is equal to 1, NOR gate x plus y whole bar is equal to 0. Next, RHS left side negative AND gates where inputs is x, y variables, output is x bar into y bar, x bar into y bar. Case 1, x is equal to 0, y is equal to 0, negative AND gates output is x bar into y bar, that is equal to 1. Second condition, x is equal to 0, y is equal to 1, and negative AND gate x bar dot y bar, answer is 0. Third condition, x is equal to 1, y is equal to 0, negative AND gate x bar into y bar, the resultant output is 0. Then last condition, x is equal to 1, y is equal to 1, negative AND gate x bar dot y bar, the resultant answer is 0. Where comparing LHS output and RHS output, that is equivalent. Therefore, DeMorgan's second theorem constructs these logical circuits and verify with the help of the truth table. Verify with the help of the truth table. Has standard DeMorgan's theorems also apply to expressions in which there are more than two variables? The following example illustrate of the applications of the DeMorgan's theorems, 3 variables and 4 variables expressions. For example, applying DeMorgan's theorem, expressions of the 3 variables, that is input variables is x, y, z. DeMorgan first theorem's expressions is x, y, z whole bar is equal x bar plus y bar plus z bar whole, x plus y plus z whole bar. That is x, y, z whole bar is equal to x bar plus y bar plus z bar, or x plus y plus z whole bar is equal to x bar into y bar into z bar. This is a DeMorgan's second theorem. DeMorgan's second theorem's expressions is x plus y plus z whole bar is equal to x bar into y bar into z bar. For example, DeMorgan's theorem to express in 4 variables, that is x, y, z, w, x, y, z, where w, x, y, z is inputs variables. The DeMorgan first theorem stands for the 4 variables is x, y, z whole bar is equal to w bar plus x bar plus y bar plus z bar. At the same time, DeMorgan's second theorem stands for the 4 variables. Expressions is w plus x plus y plus z whole bar is equal to W bar into X bar into Y bar into Z bar. This is a De Morgan second theorem expressions. Next, applying De Morgan's theorems. Apply De Morgan's theorems. The following produce a related of the applications of De Morgan's theorems. The Boolean algebra to the specified expressions, that is a plus b into c bar it whole bar plus d into e plus f bar into whole bar and whole bar. Step 1, calculation of the above problems simplifications is step 1, identify the terms of the which can apply De Morgan's theorems, and think of the each terms as single variables. Let a plus b into c whole bar and bar, and x stands x and d, and e plus f bar whole bar is equal to y. Since x plus y whole bar is equal to x bar into y bar, then simplification of the above equations, a plus b c bar whole bar plus d into e plus f bar whole bar is equal to a plus b into c bar double bar into d into e into f whole bar. Where step 3, using rule 9, a double bar is equal to a, to the cancel the double bar over the left terms. Hence, this is no part of De Morgan's theorems. That is a plus b into c whole double bar into d into e plus f bar whole double bar is equal to a plus b in a plus b into c whole bar into d into e plus f double bar. Applying De Morgan's theorems in second terms, a plus b into c whole bar into d into e plus b bar whole double bar is equal to a plus b into c bar into d bar plus e into e plus f bar whole double bar. They're using ninth rule. A double bar is equal to a, and cancel the double bar of the over the e plus f part of the terms. That is a plus b into c bar d bar plus e into f bar double bar, that is equal a plus b into c bar and d bar plus e plus f bar. Next, this ఈ విధంగా మనము simplifications చేసుకోవాలి. Example for the De Morgan's theorems, each following expressions. That is, first one is a plus b plus c into d whole bar. Second one, a b c plus d e f whole bar. C, a into b bar plus c into d bar plus e into f whole bar. Example, the Boolean expressions for an exclusive OR gate is a into b bar plus a bar into b. which this as a starting point. Use DeMorgan's theorems and any other rules of laws of they applicable to the development expressions for the exclusive OR gate. Exclusive OR gate. Boolean analysis of the logical circuits. Boolean algebra provides a sequence ways to express the operation of a logical circuit formed by a combination of logic gates so that the output can be determined for the various combination of inputs values. Boolean expressions for a logical circuits. To derive the Boolean expressions, Boolean expression for a logical circuit. To derive the Boolean expression for the given logical circuit, begin at the leftmost input and work towards the final output, writing the expression for each gate. For example, the circuits of logic gates, that is OR gate, AND gate, NOT gate, NAND gate, NOR gate, exclusive OR gates, etc. The Boolean expressions is determined as follows. The expressions for the leftmost AND gate with inputs C and D is CD. The output of the leftmost AND gate is one of the input to the OR gate and B is the another input. Therefore, expressions for the OR gate B plus C. Next, the output of the OR gate is one of the inputs to the rightmost AND gate and A is other inputs. Therefore, the expression for the AND gate is A into B plus C, which is the final output expressions of the entire circuits. This is a logical expressions where first to put in take inside the AND gate inputs C and D. The resultant of the output to AND gate is C into D. The resultant of AND gate output is taken as another input of the OR gate another input B. Then total output of the OR gate is B plus C into D, where total output of the OR gate is taken as input of the another AND gate and another AND gate of input is A. Then the total the output is A into B plus C. A into B plus C. The logicals showing the development of Boolean expression for the output. Constructing a truth table for a logical circuit. Logical circuit. One of the Boolean expressions for a given logical circuit has been determined a truth table that shows the output for the all possible values of the input variables can be developed. The produce required that you equivalent of the Boolean expressions for all possible combinations of values for the input variables. In the cases of circuit, there are four inputs variable, that is A, comma B, comma C and D, and therefore 16, 2 into 2 power 4 is 16 combination of the variable possible. 2 into 2 power 4 is equal to 16 combination of the variable possible. Putting the resultant truth table format. The first step is to list of the 16 inputs variable combination of is 0 and 1s in a binary sequences as shown in table. Next place is in 1 in the output column for the each combination of input variables as is determined in the evaluation. Finally, place of the 0 in the output columns for the other combination of the variables. The resultant showing through the tables. This is the four variables and 16 operations of the will be there, where A, B, C, D are inputs variables. The possible of the combination of variables of the possible of the variables is 2 power 4 is equal to 16. 16 variables. This is the topic of the DeMorgan's theorems and application of the DeMorgan's theorem.